Tonight we're going to be looking at complex numbers and doing some solving some problems with complex numbers and equations of complex numbers. So let's define what a complex number is. Last time we defined what an imaginary number is. Tonight we're going to be defining a complex number. So generally we denote z to be our complex number, and it's anything of the form x plus I y. I need to sneeze, sorry. X plus I y is a complex number. Where x and y are real. Now we say that the real part of z is the real z, and this is x. So x is the real part, and the imaginary part z is y, and we call it the no, it's not real, it's imaginary part of z. So this is the real part and this is the imaginary part, even though we call this the imaginary part because it's associated with the value of I, but remember y is a real number. So when x equals 0, z is just going to be I, y, so it's completely imaginary. And when y equals 0, z is just going to be equal to x, therefore it's completely real. From this we can then see how the different sets of numbers relate to each other. So let's just draw all numbers belong in the complex. Let's just write z equals x plus I, y. So all numbers belong in the complex set. And we can have a subset here of imaginary numbers when x is 0. Then we have our real numbers. So this is when the real numbers is when y is equal to 0, z is just going to be equal to x. Then we've got our set of Q are rational numbers, so these are all our fractions. Then we have our, we'll make that a bit bigger because we need to draw more inside it. Then we have our set of integers. So integers are anything for minus numbers and positive numbers, 1, 2, 3, 4, 5, minus 1, 2, minus 3, minus so on and so forth. And then we get our natural numbers. So these are natural numbers, and we can have our natural numbers including 0. But remember from our last time we discussed how originally we didn't have a 0. It was just the natural numbers that you can use to count things like 1, 2, 3, 4, 5 goats in your herd, and so on. So this is how the different number categories kind of sit with each other. Now, let's imagine we have complex numbers z1 equal to x plus I, y, oops, I didn't write properly, and z2 equal to a plus I y. Now x1 equals x2 if x equals a and y, oh sorry, that's not meant to be a y there. It's meant to be a b. And y equals b, which seems quite logical. This then leads us on to the complex conjugates. So if we had z equals x plus iy, and then we had, so we'll call this z1, and then z2 equals x minus iy. So our imaginary part is the negative value. We've got positive y and then negative y. So these are not the same number. These are two different numbers because although x equals x, y doesn't equal y. What we call z2 is actually equal, is what we call the complex conjugate, and it's given this notation, either a little star or it's equal to z with a little bar over here. So this is the complex conjugate. So z equals x plus iy, and its complex conjugate equals x minus iy. Okay, now let's do solve some equations involving complex numbers. So we're going to solve the following. We're going to solve 5z squared plus 14z plus 13 equals 0. Now this looks like any quadratic equation that you would have done previously. It's the same format, and we in fact solve a quadratic equation involving complex numbers in exactly the same way as you would if it had real numbers. Looking at these are not very nice, so we're going to use the quadratic formula. So A is going to be 5, B is going to be 14, C is going to be 13, so Z is going to be minus B plus or minus B squared minus 4AC over 2A. So shoving your numbers in, minus 14 plus or minus 14 squared minus 4 times 5 times 13 all over 2 times 5 is 10, and that's going to give us minus 14 plus or minus 14, not 14, sorry, looking at the wrong number, minus 64, if you work all that out, over 10. This is a negative number. It's a square root. Now previously, when you did a quadratic equation, you would say this has no solution. But now we've been introduced to complex numbers, we can find a solution for this quadratic equation in the as a complex number. So we've got minus 14 plus or minus. This is 64 times minus 1 over 10. Now the square root of 64 is 8. I'm going to write it up here. So Z is going to be minus 14 plus or minus 8i over 10. So that tells us that Z is equal to minus 7 over 5 plus 4i over 5, or, make that a better I, or minus 7 over 5 minus 4i over 5. Now note, minus a positive, the two roots are complex conjugates of each other. Let's solve another equation. So we've got 2x plus y plus y minus 5 equals 0. And we want to find values for x and y. So here we've got a complex number and it's equal to 0. But what this means is x plus y, this is the real part, plus our imaginary part equals 0, but the real part must equal 0 plus the imaginary part. So now we can equate the real and the imaginary to 0. So this is going to be equation 1, and y minus 5 must equal 0, and that's equation 2. So we can solve equation 2, y is just going to equal 5, and now we can substitute into equation 1, which gives us 2x plus 5 equals 0. So then x is going to be minus 5 over 2. So we can also do calculations involving complex numbers. So we're going to look at the rules for calculations with complex numbers. And to do this, we're going to take two complex numbers and use them as examples. So we've got z1 is equal to 2 plus 3i, and z2 is equal to 8 minus I. So let's do addition first. So we want to do z1 plus z2. So we'll write z1 is 2 plus 3i plus 8 minus y. So we do this in the same way as we would if we were working with any algebra. We just collect like terms. So the real part is 2 and 8, so 2 plus 8 is 10. The imaginary part is 3i minus I, which is going to be plus 2i. Subtraction is going to work exactly the same way. Oops, no, draw it right there. So z1 minus z2 is going to be 2 plus 3i minus, now put this in brackets so we keep track of our signs. So we've got 2 minus 8 is going to be minus 6. 3i minus 1 is going to be plus 1, is going to be plus 4i. Now we're going to do multiplication. So we've got z1 multiplied by z2. So we line under that. So we've got, so we'll put them in brackets. So z1 is 2 plus 3i, and we multiply it by 8 minus I. So this looks familiar. This just looks like what we'd have if we were expanding out brackets, and we do it exactly the same way. So we've got 2 times 8, which is 16. 2 times minus I is going to be minus 2i. 3i times 8 is going to be plus 24i. Then 3i multiplied by minus I is going to be minus 3i squared. So the I is going to be squared. So remember, I squared is minus 1. So now we gather like terms. So we've got 16, and that's going to be minus 2i plus 24i, which is going to be plus 22i. And this here is going to be, we've got minus 3, but we've got times by I squared, so that's going to become minus 1. That's then going to become plus 3. So for completeness here, we've got 19 plus 22i. Let's look at, actually I'll take a new page actually because we're running out of space. So I'm just going to write Z1 again, which is 2 plus 3i. Z2 equals 8 minus I. So let's think about what happens when we multiply the complex conjugates together. So we'll just use Z1. So in exactly the same way as before, we've got 2, this looks like a Z, I'll change that, 2 plus 3i multiplied by 2 minus 3i. So we've got 4 plus 6i, 2 plus, minus 6i, sorry, I'm making a mess of it, minus 9i squared. So, plus 6i minus 6i, they're going to cancel. So we're going to have 4 minus 9, I squared is minus 1, minus 9 times minus 1 is going to be plus 9, so that gives us 13, which is a real number. And this leads to an interesting fact. So if we've got z equal x plus iy, and the conjugate is x minus iy, z, oops, let's do the wee starry thing, z times its complex conjugate will always lead to a real number, and it will be x squared plus y squared. So a real number. And that's pretty easy to prove just by multiplying these together the same way we did that, just doing the general form. So that's our multiplication. Now we can look at division. So z2 divided by z1 is going to be 8 minus I over 2 plus 3I. So the first thing that we do is we multiply the numerator and the denominator by the complex conjugate of z1. So this will give us 8 minus I, 2 minus 3I over 2 plus 3I multiplied by 2 minus 3I. And you can see why we're doing that, because that's going to give us, instead of a complex number on the bottom, we're going to just have a real number on the bottom. Let's do the top one first. So that's going to be 16 minus 8 times 3i is 24i minus 2i plus 3i squared. And that's going to end up being x squared, which is 4, plus 9, which will give us 13. Tidying this up, I squared is going to be minus 1, so Doing all that, we'll get 13 minus 26i over 13. Oh, sorry, it's not 13, there's 16. Well, it's 13, sorry. And that then gives us 1 minus 2i as our answer. So I hope that helps.